we have discussed the capacitance of a MOSFET and how it behaves in weak inversion and how it behaves in strong inversion regimes previously. So, today we will now discuss the appropriateness of charge sheet approximation, because this is what we will be using in general. So, how is it justified? So, what is the total inversion charge looking from the top? In this, if we look from the top, what is the total inversion charge that you see? So, it has a density given by this, isn't it? So, you are just integrating from in the y direction from 0, 0 is in the neutral region, 0 to the interface. So, also that is why you are saying infinity, in the sense that because there is a limited silicon. So, infinity does not matter, it is actually the interface, that is what you mean to say here. But how can you want to convert this into the limits of the integral into potential. So, what would you do? So, you can also use this fact that Ez can be given as the derivative of potential, is not it? So, that is what you use here. You say that this is so, this is what you are doing. So, this gives me this x. So, from this you arrive at this expression. So, now you have converted the limits from z to potential. Let us look closely at this function. So, is it important to integrate from 0 to chi s? So, if you are using charge sheet approximation, you would say that the charge is almost entirely concentrated at the interface. So, in fact, you do not need to integrate from 0 to chi s. You may integrate just very in the vicinity, very close to chi s, is not it? So, that would justify. So, we will try to understand whether this justification is valid or not. So, how does this function NP by Ez behave with respect to potential? So, potential is now 0 here and chi s here, surface potential, and in between it is chi, it is having a value. So, you would see that as you increase chi s, how does this f function, the function f, how does it behave? So, you are operating in depletion and inversion regime, is not it? So, because we are looking at weak inversion, moderate inversion and strong inversion. So, this term which is related to accumulation, as we had discussed earlier, is not important for us. So, we are left with the other two terms. So, if the value of this chi, if you are increasing the value of chi, so you are increasing it from neutral region as we go towards the interface. So, if you are increasing the value of chi, which is the potential, so you would so this term would exponentially increase, this term would linearly increase, is not it? And so, you may in depletion regime, we know that this first term would be negligible compared to this. So, this would NP by Ez in depletion regime would look would be proportional to minus V by ut divided by ut, is not it? So, you will find that this is as if NP by Ez is proportional to exponential chi minus 2 phi f. If you neglect, if you imagine that the exponential term would dominate and the square root of chi minus ut would be a slow varying function, you would say that essentially this is what is valid. So, in depletion regime. So, you would so what you find is that NP by Ez, when you plot it along chi by ut, NP by Ez, a normalized value here, this is normalized, just you have normalized it with respect to NP by Ez with respect to this. So, here you find that when the depletion in weak inversion or moderate inversion, when the depletion approximation is depletion charge is much larger than inversion charge, the denominator is given by this, f function reduces to this because this is negligible, this term is negligible compared to this. So, therefore, you would essentially see that NP by Z roughly almost looks like this. So, what is happening? So, here you have a function of the form exponential chi minus 2 phi f, if v is 0, exponential chi minus 2 phi f mvt divided by mvt, where m is equal to 1, is not right. So, now let us see what happens in strong inversion. So, when strong inversion sets in, NP by Ez would be proportional to divided by this divided by function f. So, in function f, now in strong inversion, in function f, this term dominates compared to this, because this has become larger than, so chi has become larger than 2 phi f plus v. So, that is why this term now starts dominating compared to this. So, you would have exponential. So, approximately, so you just neglect this 1 here, you neglect the term 1 here, this you neglect. So, what is this equal to? Minus v divided by 2 ut. So, here you have m is equal to 2. So, therefore, you find that when strong inversion sets in for larger values of chi by ut, you have a smaller slope here. This is logarithmic scale. So, here you have a larger slope and here you have, in the weak and moderate inversion you have a larger slope, in strong inversion you have a smaller slope. So, what you see is that as you increase, as you change the value of chi, that is as the value of potential reduces, when you go from the interface towards the neutral region. So, as the potential increases, reduces, you would find that in moderate inversion or weak inversion, the rate at which the inversion charge density falls is stronger than what happens in strong inversion. So, what you are saying is that the inversion charge density anyway falls, because inversion charge density is given by this term, and as the value of potential reduces, this term reduces, the inversion charge density anyway falls as you move from the inversion towards the neutral region, down, vertically down. So, but it reduces faster in weak inversion than in strong inversion. So, in that sense, this charge sheet approximation should be more, valid in strong inversion, in weak inversion, I am sorry, approximation is better valid in weak inversion. Now, let us look more closely at charge sheet approximation. So, what we have done here is, as we were discussing, so this is chi s, the potential chi s, and here you have some potential chi. Okay. So, in this, if the drain voltage is 0, you have quasi equilibrium. Even otherwise, very close to the source, you know, it is like the band diagram would be like quasi equilibrium condition itself. That we had discussed earlier in the course. So, we had written that the inversion charge density at any point z is Np, which is the neutral region's electron density exponential. This we had discussed, that isn't. So, if you are, so what is the charge density at the interface? So, at the interface it will be, suppose Ns, let us call it Ns at the interface here, the charge density. So, what would that be? That would be exponential chi s minus 2 phi f minus v by ut. So, what would be the charge density, say a distance. So, from here till here, suppose it is delta z. So, a distance z, delta z below. So, you are saying you are going down by delta z, and that also reduces the potential, from chi s to chi, suppose. So, in that case, what is the value of n at when you go a distance delta z below the interface, So, what is that? So, that is Ns exponential chi minus chi s by ut. This we have derived from. So, you can derive this from both these expressions. From both these expressions you get this. So, that is what we are now plotting That is what we are now plotting on the y axis. So, it is n of delta z. So, as you move delta z down, what is the change in charge? So, with delta z, when you move delta z vertically down from the interface, you change the potential from chi s to chi. The potential changes from chi s to chi. So, with this change in potential, what is the change in inversion charge density? So, now this is inversion charge density per centimeter cube. Okay. So, this is what it is. So, now let us look at it more carefully. Suppose the change in, so what we will verify this, we will also verify this with some example calculations. So, as you move, as you reduce the potential from here to chi, so the chi's value is -1, -1 means minus ut. So, this is minus ut, which is 26 millivolt below the interface potential, which is chi s. So, 26 millivolt below chi s, it is the value of inversion charge density is this much. What is it? 1 by E. If m is 1, it is 1 by E. Okay. Like that, here it is 1 by 2 E if m is 1. M is 1 in moderate or weak inversion, as we had seen earlier. So, so what we are seeing is that for small, a very small reduction in surface in potential, when you move below, a little below the interface, you find that the inversion charge density reduces by a large amount. So, this suggests that the charge sheet approximation is quite accurate and we can use it in our further work. So, now let us look at the depletion charge density. How much is the depletion charge density in this? So, in the f function, we had seen that in moderate and strong inversion, it is the only the linear term chi s by ut remains, and the exponential terms, one is because of accumulation charge, which is anyway negligible, and the other one is because of inversion charge. In weak and moderate inversion, that term also is negligible, and therefore, only the linear term remains, and therefore, this is, we find that this is what remains for inversion charge. So, we have integrated the f function. So, this whatever is in the this square root term is actually proportional to f, as we had seen. So, f function in moderate inversion. Okay. So, if this is, so now we define this as some gamma b Cox into square root of chi s. So, what is then this? What is the value of gamma b then? From here you would find that it is epsilon silicon by Cox, because you have multiplied Cox here, divided by L d into, you have a square root of ut here. So, therefore, it becomes square root of ut. So, how much is the value of this? If we calculate, it is 11.9 silicon's relative permittivity to 8.854 minus 14 farad per centimeter, volts 0.026 volts, which is ut, divided by Cox. Cox we had calculated earlier, and LD also we had calculated early in our earlier lectures. So, that becomes 10 to the power minus 6 into 0.29 into 10 to the power minus 6 centimeter. So, this comes out to be 1.7. Now, what is the unit of this? So, unit of gamma b is square root of b divided by farad per centimeter. It would come out this way, because so, and right. So, what? So, this is a substrate modulation factor. So, how does it affect? If the value of gamma b is larger, how it would be larger if the body substrate doping density is larger. So, if this is an n channel MOSFET. So, if the p type substrate doping density increases, then the value of gamma b also increases. So, here you have just substituted the value of LD. So, that is how you get this. So, value of substrate modulation factor, it increases as you increase the substrate doping density. So, what implication does this have? So, for the same value of surface potential, you have a larger depletion charge density, or in other words, for if you do not change the gate voltage, then if the substrate doping density is larger, substrate modulation factor is also larger, and therefore depletion charge would tend to be larger. So, if you do not change the gate voltage, the value of surface potential itself would reduce. So, that is how this is related to surface potential. So, what is the value of depletion charge density? If for this value of surface potential, what is the value of depletion charge density? So, let us first look at what is 2 phi f. So, let us look at the depletion charge density at the edge of inversion region. So, which is when chi s is equal to 2 phi f. Okay. So, how much is that value? That is 0.94 volt from here. So, what is the value of depletion charge at that for the edge of strong inversion and moderate inversion regimes when chi s is equal to 2 phi f. So, there the value of this is 1.7, which is gamma b into, that is surface modulation factor, into 0.345 into 10 to the power minus 6 into square root of surface potential, which we are saying is 2 phi f. So, that is 0.94. So, how much is this? It is approximately 0.6, just to get a feel of numbers. And what is the value of, yeah. So, from here now let us also see one interesting point, that what is the value of inversion charge density n for m is equal to 1, which is moderate or strong inversion condition, and this is minus 2, which means that chi is that you have gone down to from the interface, you have moved down vertically to a value or to a point z, where the potential has reduced by 2 ut, which is at room temperature 0.052 volts, that is 52 millivolts. So, you have moved down 52 millivolts. So, what is the value of n there? So, now this n is e to the power minus 2. So, this is e to the power minus 2. So, e to the power minus 2 times whatever it is at the interface. So, e to the power minus 2 means how much in percentage terms you would say that it is 13%, approximately 13% of the value here. Here it is 100%. So, whatever is the value of inversion charge density it is here, you will have 13% of that value here. So, how much below the interface is this? So, we know that change in potential can be related to change in distance. So, that would be q n b delta z square divided by 2 epsilon silicon. So, from this you can, this is from the Gauss law, which we had discussed in the beginning of the course. So, from this you can say that the change in the distance delta z below the interface, how much. So, you relate it to change in potential as you go vertically down from the interface, that would be 2. Okay. So, for 52 millivolts, if you substitute values, this turns out to be nearly 0.84 nanometer. So, what you are saying is that as you move 0.84 nanometer below the interface, 0.84 nanometer from the interface, that is at nearly 1 nanometer below the interface, the inversion charge density reduces to 10%. So, of its value at the interface. So, whatever is the inversion charge density's value at the interface, it reduces to about 10% or 13% here. So, as you move just nearly 1 nanometer below the interface. So, that shows that charge sheet approximation is quite valid, because this 1 nanometer is negligible compared to the depletion region's width. So, it occupies negligible part of the depletion region as you move below the interface, vertically below the interface. So, today we have discussed charge sheet approximation and why is it valid and why we can use it in our further work. Thank you.